Hello everyone, this class is BSML 7247 Analysis for Macromarketing Data. This video is for Lecture 7, Fixed Effects and Seasonality. For this lecture, we don't have any reading requirement. In this lecture, I am going to first introduce fixed effects and how to handle the fixed effects in real data by using dummy variables. Handling fixed effects is sometimes very important in analysis because omitting the fixed effects can lead to a large bias in the estimate of other effects. This bias is called omitted variable bias, and I will explain what it is and why it appears. Then I will explain how to use the concept of the fixed effects and dummy variables to control for seasonality. Fixed effects. In general, if a statistical model has only fixed model parameters, then the model is called a fixed effect model. Usually, a fixed effect model is used to analyze data with several groups that have different group means. Here is an example. This is the Mr. Mistake and Ms. Perfect data. The data are two-dimensional, having sales and price information for each brand and week. A fixed effect model assumes that the mean or baseline sales varies across the brands. Here we have two subscripts J and T. J denotes brand and T denotes time. Then the baseline, denoted gamma, varies across the brands. That's why gamma has subscript J, meaning that gamma is J specific, that is brand specific. What does that mean? For brand A, its baseline coefficient is gamma A. For brand B, its baseline coefficient is gamma B, which is different from gamma A. For brand C, its baseline coefficient is gamma C, which is different from gamma A and B. Across the brands, price effect is common, but each brand has its own mean or baseline level of its sales. For better understanding, let me show the details of the data structure. As I mentioned, the data are two-dimensional, brand and time. So, each observation is associated with a unique brand-time pair. That is, there are brands A, B, and C sales and price data over the weeks in the data. And this table is the conceptual image we have about the data. But the actual data is stored differently from the two-dimensional image. The dataset is actually unidimensional, and let's say this dimension is the observation dimension, denoted subscript I. Instead, each observation contains information of the two dimensions. So for example, observation 1 has the data of brand equal to A and time equal to June 6, 2005. That is, we have the following correspondence. An observation I is corresponding to a unique brand time pair, J and T. The brand and time variables give us which brand and time the observation is associated with. So, we rewrite the fixed effects model as the model of a unidimensional data set. Each brand time pair, JT, is simply replaced with each observation, I, and the brand subscript, J, is replaced with the brand variable, the brand I. Now, this gamma is a function of the brand variable, that is, the value of gamma depends on the brand variable. Using dummy variables is a smart way to operationalize this redimensioning. The key of the redimensioning is how to operationalize this gamma function that depends on the brand variable. Mathematically, this function is the exactly same as this formula. Here, this I denotes an indicator function, so if the input of an indicator is true, the indicator has 1 as its value. If not, it has 0 as its value. and a variable created by this indicator function is a dummy variable. For example, if ith observation is associated with brand A, then only the first indicator becomes 1 and the others have 0. Gamma A times 1 plus gamma B times 0 plus gamma C times 0 equals gamma A. So we end up with having the correct baseline parameter for brand A. This is a snapshot where the dummy variables were created. For convenience, DA, DB, and DC are the dummy variables for brand A, B, and C respectively. Then the fixed effects model is the same as this unidimensional regression model with dummy variables. These gammas are the dummy variable coefficients to be estimated. But we have one more step. A regression model generally requires a common intercept for all observations. So let's do the math. This is the fixed effects model on the unidimensional space. For brand B and C, just subtract gamma A from their coefficients and add gamma A to them again. This doesn't change anything. And rearranging the terms, we have all terms with gamma A. And here's a trick. Sum of all dummy variables is always equal to 1 because only one of them has 1 and the others have 0 at every observation. So, finally, we have this regression model with a common intercept. This common intercept captures the baseline. In this case, brand A's average is set to the baseline. The coefficient of the dummy for brand B captures not the brand B's average, but the deviation of brand B's average from the baseline. The coefficient of the dummy for brand C captures the deviation of brand C's average from the baseline. Fortunately, R has a good function to execute this strategy. As factor function in LM creates dummy variables and adds the dummies into the regression. So left-hand side table is the result from the regression using as factor function, and right-hand side table is the result using the dummy variables that I made. As you can see, all results in the left are identical to those in the right. Then, why consideration of the fixed effects is important? Please recall the Mr. Mistake and Miss Perfect example. The brand effect was missing in the Mr. Mistakes analysis, and adding the brand effect make the positive coefficient turn negative. That is a typical example of an omitting variable bias. Suppose the following true process, but the dummies were missing in the model estimated. Then B, which is the estimate of the price coefficient, significantly deviates from its true value if the omitted dummies are highly correlated to the price variable. The left-hand side table is the regression summary with the brand dummies, and the top right table is the regression summary without any brand dummies. And the bottom right table is the correlation coefficient between the log price and the dummy for brand C. If dummies are omitted, we have positive price coefficient about 1.87. But this value is the sum of the correct price coefficient and bias, which are negative 1.09 of the price coefficient and about 3 of the bias. This bias really big, and it is coming from this very high correlation coefficient between the dummy and prices. There are no exact formula to compute the omitted variable bias, but we can roughly expect the sign of bias based on the sign of the correlation and the sign of omitted effects. Let me go back to the Mr. Mistake and Miss Perfect example. Brand C's price level is much lower than brands A and B's prices. The dummy variable for brand C has 1 if an observation is for C. That is, price goes down if dummy for brand C changes from 0 to 1, indicating a negative correlation. Although brand C was cheap, market share of brand C was not that high, mostly low. That is, the omitted brand effect for C is negative. As in the table, in this case, omitted effect is negative and the correlation between the omitted and remaining variables is negative. Thus, positive bias is expected, and we found the positive bias from the estimation in the previous slide. Then, why? Omitted variable bias can be viewed as a confounding effect. The brand effect is negative, and the brand is highly correlated to price. That is, the brand effect is also highly correlated to price, leading to the bias. Thus, the higher the correlation and the stronger the omitted effect, the bigger the bias. The concept of the fixed effect is useful to control for seasonality. Seasonality is defined as follows. An event is seasonal when it happens periodically, that is, at regular occurring intervals. For example, this is beer sales data across 9 different stores. There are many differences in the sales between the stores, but the overall trend is very similar, and several periodical events were found. In summer, beer sales periodically surge, like these points. Also, we found that beer sales surge too in Christmas season. There are various methods to model the seasonality. A group of methods is time series analysis, including RMR, HMM, wavelet, and etc. Those models rely on periodical patterns in historical data, like that something happened 12 months ago happens again. That is, those models focus on identifying the periodical interval from data. Another way is to use dummy variables. We can create dummy variables for all events that periodically happen prior to analysis. To control for the seasonality, we may put all of the dummies, and for each seasonal event, this approach focuses on the average effect size over time. This is the data set of your sales where were plotted. From the data information, we can extract the week number, and using as factor function, we have all of 52 weeks effect. Seasonality control is important because firms decisions like pricing and sometimes highly correlated to seasons. These two figures show weekly trend of demand volume and average price for ready-to-eat canned soup. The green area indicates the off-season, which is summer. As in figure 1, demand volume is relatively super low during the season. But as in figure 2, during the summer, the soups were sold at a relatively high price level. Thus, if the seasonality is missing in analysis, we may have only the variable biases due to the highly correlated coefficient between the price and seasonality. Then, how to determine the seasonal granularity? There are no clear rules and no rule of thumbs. In general, if seasonality is coarse in analysis like monthly or quarterly dummies, interpretation of the seasonal effects is clear and straightforward. But the seasonal effects are highly likely to be smoothed out. Of course, the Black Friday sales increase is reflected in November and December sales level, but the peak sales and the peak price discount information during the Black Friday week is highly likely to be washed out. On the other hand, if seasonality is fine in analysis like daily or weekly dummies, we can fine-tune various seasonal effects. The Black Friday week is separated out from the other weeks, and we can exactly control for the Black Friday changes. But the fine-tuned seasonality also faces a problem. For each seasonal effect, like week 1 effect, week 2 effect, etc., the number of observations could be too small, implying that there is a possibility to be confounded with outliers. Alright, that's all I have in this lecture. In exercise, you are going to analyze beer sales data. Then, see you in the next lecture. Bye bye.